Good morning one more time. Now we need to talk about the covalent bonds. We talked about ionic bonds last time, and we said that a bond is ionic if the difference in this here electronegativity number between the two elements which are bonding is bigger than 1.8. However, the actually more common bond is covalent bond. So covalent bond is, you can see there are two types of covalent bonds. There's polar covalent and non-polar covalent. So basically, as you go here, you can see that if the difference in electronegativity is under 1.8, that's called polar covalent bond until you get to 0.5 in most books. Again, that number varies. So under 0.5 is called non-polar covalent bond. Basically, if you look at these numbers here, you will notice that if you connect, say, I don't know, H and Cl or H and F or similar elements like that, which are on the plus side with those that are on the minus side of the periodic table, you'll see that most covalent bonds are actually polar. You do need to remember some bonds which are not polar. And that's number one, bonds between the same elements. So gases usually form the bond with two atoms of the same gas making a bond. So H2, N2, O2, F2, Cl2, Br2, I2. Those are the most famous non-polar covalent bond, most used. And another one which is really important is the non-polar bond between C and H. Look at the electronegativity difference and you will see that the bond between C and H is also non-polar covalent. And this is really important because this bond is very, very common. You need to remember that. Okay, the second thing that we need to remember is that the ionic bond is a transfer of electrons from one element to another. So the electron with the lower electronegativity gives one or two electrons and they move to the other element or elements that are they have a high electronegativity. That's an electron transfer. However, for covalent bonds, we don't have that. There is no electron transfer. There is electron sharing. So the orbitals of the neighboring two elements overlap and create the bond. The easiest way to describe this is by using an example of Cl. So Cl forms this molecule called Cl2, which is made of two atoms of Cl. So let's analyze that. So you've got one Cl, and Cl is in group 7, so it's got 7 electrons in the last energy level. So this is going to be its electron dot diagram. And this is the other one. So here, assuming both of them, as they do, want to achieve a stable configuration of 8. If you move this one here, you're not achieving stability. You're achieving stability for this one, but not for the other one. So the only way that they can achieve stability is to share this electron. Oh, that's horrible. That's just horrible. To share the electron with each other. So now these two electrons that are in this bond, they're counted on both sides. So this one has 8 electrons, right? And this one also has got 8 electrons. And now they're both happy. Both Cls are happy and they're stable. However, I want you to know exactly how this happens. So the overlapping of the orbitals is really important to understand. You will see for later. This is not something that they will ask specifically in AP questions, but they will ask a bunch of other things which you will know how to answer if you know this. So actually learning more about orbitals and in a deeper way is going to make your study time shorter and your understanding much deeper. So let's look at Cl. So group 7, period 3. So that means that on this side you've got 3s, which is full, right? And you got 3p, which has got 5 electrons, right? So this, note how these electrons, when you write them here in the Lewis structure, they're always in pairs. Why these electrons always drawn like this in pairs? Because they are in pairs in orbitals. So this, always try to put them in pairs just like they are in the orbital so you can better understand. And now the second Cl, let's draw it in reverse. So let's say this is 3s of the second Cl, and then you got the 3p orbital of the second Cl. So what happens now, it shouldn't be drawing up and down, should be up, up, but okay. So these two orbitals basically overlap like this, and they become one orbital. So this is actually this line. However, how this looks like in 3D is not really like this. To know that, you need to know how the orbitals look like, and this is really important. Again, we explained why. So let's explain each orbital. The s orbital is the easiest to explain. So an s orbital is just a big sphere. And according to relativistic physics, according to Niels Bohr, Heisenberg, Einstein, and so on, we cannot know how the electrons move. We don't know if they're moving in a circle or in a shape of 4 or 6. We don't know that. But we do know they are inside this space. So any electron in s orbital is inside this circular, spherical, actually, space. So one s orbital is a sphere. However, most elements also have two s orbital, which is also a sphere, just a bigger one. So you should imagine it like this. If an electron is in 1s orbital, it should move inside this sphere. If an electron is in 2s orbital, it should move in this sphere. So they even might be in the same place, but inside that sphere. So as you go up, you can see up to level 7, the spheres just get bigger. So something that has 1s and 2s orbital, it's got both of these spheres. And 3s has all three of them, and so on. So s orbital, easy to remember. P orbital, not so easy to remember. Please ignore this plus and minus. This plus and minus have nothing to do with actual charge of plus and minus. This is just showing the side. It's something connected to relativistic physics, which we don't need now. So we have only one s orbital in each energy level, right? But we always have 3p orbitals, right? This is how they look like. So this is 2px. 2px is just, we draw this usually as a number 8 on the x-axis. 2py is the same shape on the y-axis, and 2pz is the same shape on the z-axis. So p orbitals look kind of like an infinity sign. D orbitals are even more complicated. They're not going to ask you probably to draw any overlap of the orbitals, but again, you should know how they look like for the future. So it's actually easy to remember. They look funky, but they're easy. So look at this. dxz is basically a flower between x and z axis. dyz is this same shape between y and z axis. dxy is this same flowery shape between x and y axis. dx squared minus y squared is this shape, but now not between the axes. Now it's on these two axi, x squared and y squared. And dz squared is easy to remember because it's just funky and weird. So again, mostly we're gonna be using when you draw s and p orbitals, so you do have to know exactly how they look like. These are useful for later. Now, knowing this, how do we draw the actual overlap? Let's see a couple of examples. So here we got the overlap between basically this p orbital and this p orbital, and these orbitals usually are on the same axis because the empty orbital is always the one which is again not important for right now. So basically this is one Cl that has, I'm just drawing this orbital, so this is this orbital. So again, it should really look like this, but I'm just trying to be fast. So this is an orbital of one Cl, this one, and here we're going to draw another one, and they're overlapping. This is just a horrible picture, but you see my point. So two infinity shapes basically, and the electrons are here. These two electrons are here. So this space here is the actual overlap of the actual bond. So we never draw any other stuff here because let me just wipe this off and try to illustrate something else. So basically we've got one p orbital and another p orbital overlap. So we only drew this one that overlaps. If we are to draw all this this is going to look weird because, see, this is another p orbital which is supposed to be like this, and then this is a third p orbital supposed to be going through the screen like this, and then there's also an s orbital here, which means you're going to have to put an s orbital here. So this is how the actual so this is the s orbital, this is, say, px, py, and pz, but we don't draw that. We only draw the last orbital, which is just going to look like this. So we just draw the one which is overlapping, and then this is and again, this is a horrible shape. This should be on the same axis like this, but doesn't matter. If we try to do something else, let's try something simpler, easier to draw for me, because you guys see I suck. Let's try H2. So one H has one electron, the other one has another, and the Lewis formula would be like this. However, hydrogen has only s orbitals, so this hydrogen will have one s orbital, the other hydrogen will have the other s orbital, and these two electrons will be in between. So this is the overlap. So you see this in 3D looks way different. And we will practice this. You don't have to pay that much attention for now. What I want to explain now is that these two electrons are exactly in the middle. Why they're exactly in the middle? Because the electronegativity of this atom is the same like the electronegativity of this atom. That's called basically a non-polar covalent bond. And again, those are H2, N2, O2, F, and everything else in group 7. And CH. Remember, CH is a non-polar bond. However, if we have a polar bond, there's a couple of tricks there. So if I have, say, H and Cl, this H, this is Cl. So what happens now is we bond it like this. And now hydrogen is happy because it's got 2 electrons, is stable. Chlorine is happy because it's got 8 electrons, is stable. But if we look here, we can see that the difference in electronegativity is now pretty big. So it's bigger than 0.8, which makes this a polar covalent bond. In a polar covalent bond, we always mark the side which has more electronegativity with a minus. This is called a partial minus, and this is a partial plus. So chlorine has more electronegativity, so that means that these two electrons are not exactly in the middle, they're moved more to the side of chlorine. Also, there is another way to draw this, which is this. You can see the logic. This is a plus, and the arrow points to a negative side. This is called a dipole. A dipole is basically something that does not have a charge as a whole, but it has a positive side. So basically this side will be positive, this side is negative. So a dipole looks like this. I mean, this is all different ways to represent a dipole. Dipoles are really important for intermolecular bonds. You will see that later. And if you want to go deeper into dipoles, you can see them here. So see, this is very similar to what I just drew. H and F, positive side, negative side. And you can see in 3D for more complicated elements. See here, oxygen has a bigger electronegativity, so it pulls the electrons to this side. So this whole side is negative, this whole side is positive. We will go into more detail about this very, very soon. Okay, practice. See you soon.